Welcome to the lectures on modern digital communication techniques. So, in the previous lecture we have seen an application of using the maximum likelihood estimator in finding the carrier phase. So, we proceed further to the general class of estimating carrier frequency for the receiver synchronization purpose. So, we have to begin with the signal parameter model, estimation model. So, we are writing the expression of the received signal as we are used to as s of t minus tau. So, here we have included the propagation delay and plus of course, there is noise which is present with us, and where s t is the real part of s l t to the power of j 2 pi f c t. So, we are used to this kind of a model. So, I am not explaining further on these models, and one could expand the s t using whatever we have here. Since it is t minus tau, we have s t minus tau, and there is a phase component associated with it now, and this phase is mainly due to the propagation delay, that is one. And since we are talking about the low pass equivalent, so what we have with us is at the transmitter you would generally have e to the power of j 2 pi f c t. This is what you use at the transmitter S L, right, and in the low pass form, sorry, this is what you have. At the receiver we would multiply this by e to the power of minus j 2 pi f c prime t. That means there is a phase, there is a difference in the frequency. So, this phase is mainly due to this delay along with some additional phase that may be due to the frequency offset, plus there may be some phase phenomena, relative phase between the transmitter and receiver oscillators. So, this should actually capture all the excess phase. So, we need to estimate the carrier phase, right. So, that means the phase has to be estimated, and we can use the ML criteria, or we can also use the MAP criteria. In the ML criteria, the signal parameter, which can be denoted as psi, sometimes it is a signal vector if there are more than one parameter. So, psi can have the carrier phase as well as symbol timing, which we will see shortly. So, it can be treated as deterministic unknown if it is maximum likelihood. If it is MAP, remember we have the prior probabilities. So, there will be the prior PDF, that means these will be modeled as random with prior PDF, right. So, that is the difference. So, that means if you have a prior PDF, you are going to use the MAP criteria. If you do not have that, then you are going to use the ML criteria. So, let us begin with the discussion of the effect of carrier phase and carrier frequency offset on the received signal. So, this is the transmitted signal at cos 2 pi f c t plus phi. So, note that there is a certain unknown phase in the oscillator, and the received signal and the received reference signal. So, that means this is what we wrote, the received reference signal. Why so? Because again reminding you about the matched filter, what do? We have R t multiplied by f k t dt. This is the component of R t. So, when you do this, generally R t is cos 2 pi f c t, that is what we have taken along with a gate pulse, right. So, what we say is that this we used as 2 pi f c t as if it was ideal situation, that is what we did before. But now we are deviating from ideal, and we are saying that no longer this has 2 pi f c t, it is 2 pi f c t prime, and there is a relative phase at the receiver. So, you could take a single phase which is relative phase between transmitter and receiver, or you could say transmitter has a phase phi and receiver has a phase phi cap. All right. So, with this justification we proceed. So, that is briefly explained over here, because we have the matched filter at the receiver, and hence if this could be a bit bigger, I think then it will be advantageous. All right. So, this is the matched filter effect that I have just explained. So, you have to take the product of the received signal along with the reference carrier. So, when you do it, So, you have the ST and you have CT. So, you have cos multiplied by cos. So, you are going to get the terms cos of 2 pi f c minus f c prime and the phase difference of the phases, and the next term would be the plus, that means cos 2 pi f c plus f c prime and addition of phases as well. So, now if you pass this signal, this particular product through a low pass filter, this having twice the frequency can be filtered off, right. So, what will be have available with you is this particular signal part. That means, we could write it as AT upon 2, this is the coefficient cos 2 pi delta f c plus delta phi. So, we can filter this off because it is at twice the frequency. The output of the matched filter considering rectangular pulse, right. So, what we remain is integration of CT/ST, that is what we have been explaining right here, that is what we have been explaining in this. So, the output of the matched filter will be, this is the product already, now the integration part is integration of AT by 2 cos of this term, that is what we have over here. So, integration of cos leads to a sine, and the inside parameter with t comes in the denominator, and you integrate this value from 0 to t, that means you calculate the value between t and 0 and evaluate it. What you get is AT by 2 sinc function of delta f c t, and there is a cosine term, right. So, if you look at these expressions, as if delta f c is 0, what do you have? You have AT by 2, and this is a 1, a cos let us assume delta phi 0 and delta f c 0. So, cos of 0 is 1. So, there is no problem. So, if there is no phase mismatch or no carrier mismatch, you are going to get the maximum value. As delta f c increases, sinc function drops like this and goes like that, and cosine function also drops in a similar fashion, right. So, what we get is these drop very fast, that means the peak of the matched filter comes down this curve at a very fast rate as the delta f increases. So, what it means is that the signal to noise ratio is reduced, the signal power gets reduced, and hence signal to noise ratio is reduced. Therefore, what we can conclude is the effect of carrier and phase offset is to reduce the effective signal to noise ratio at the receiver. Further, we will consider a double sideband suppressed carrier situation, where of course, the signal ST we have modeled. I do not know if you can zoom it a little bit, things will be better. So, we consider a DSB-SC, and this is the signal model. At the receiver we have, so we are now studying the effect of only delta phi, because there are two effects, delta frequency as well as delta phi. So, let us first study the effect of only delta phi. Now, since this is also a phase term, this is a phase absolute phase term, this is a instantaneous phase term, but of course, at time t this is the total phase. So, we can study the overall effect of a phase, right. So, to study that we are saying that let the carrier frequency be perfect, only phase effect, the effect of delta f c would be similar. So, that is why we restrict our study to phase. At the receiver, the reference signal has a phi prime. So, the product would now have half cos phi minus phi prime, because these two are going to go away and the additive terms would be filtered by the low pass filter. So, high frequency components are filtered away. So, when you pass this through a low pass filter, what we have is a upon 2 cos of phi minus phi prime. This, if we say that delta phi, this difference is 10 degrees, it will result in a loss of 0.13 dB. One can calculate, if it is 30 degrees, it would result in a loss of 1.25 dB. So, now instead, if we consider a QAM constellation, if we consider a QAM signal, we are going to have ST equals to A cos 2 pi FCT plus phi minus B sin 2 pi FCT plus phi, right. So, this is the typical expression that we have, A cos 2 pi FCT plus phi, and this is the carrier minus B sin 2 pi FCT plus phi, right. This is what we are having written in red. The reference carriers are cos 2 pi FCT plus phi prime, phi cap, and sin carrier is sin 2 pi FCT plus phi prime, because you multiply this with a cos 2 pi FCT plus phi cap, and you multiply this the sin 2 pi FCT plus phi cap, right. So, there is difference in phase in the carrier, in the cosine carrier as well as the sine carrier. So, this is at the end of the multiplication, what you get from here, that means end of multiplication and filtering through a low pass filter, you are left with A cos delta phi, that is what is here, and you are also having B sin delta phi. So, that means you are going to multiply this with cos going to one channel and this with sine going to the other channel, right. So, you have A by 2, that is how the receiver works. You have the received signal getting multiplied by cos and getting multiplied by sine, because this is cos 2 pi FCT plus phi cap, because this is your f1 of t and this is your f2 of t, that is the basis function, right. And what is coming in, going into both the things is r of t, and what is r of t? The signal component is A t cos 2 pi FCT minus B sin 2 pi FCT. Of course, there is noise. So, this is the same signal going into both the paths. So, you decode, you take the component R1, take the component R2 and then pass through the detector. So, we are looking at this point, we are looking at these points. So, the I component, that means the I channel, you are going to get A upon 2 cos delta phi and B upon 2 sin delta phi. So, if delta phi is 0, you have A upon 2, because cos 0 is 1 and sin 0 is 0, right. And the y component, the q component would be B by 2 cos delta phi. So, whichever goes along this direction would be B by 2 cos delta phi minus A by 2 sin delta phi. So, by similar reason, when delta phi is 0, you are going to get B by 2 sin delta phi is 0. As delta phi increases, your cosine term, how does the cos function look like? It decreases, right. And how does the sine function look like? It grows. So, what does it tell? As your phase increases, your desired signal decreases, it falls down, right. So, we can draw a bigger picture if you want. So, if you look at these expressions, what we have is the cos decreases and the sine slowly increases, right. That means, as we increase the delta phase, the desired signal falls. So, it has reduced the value, while the interference has also grown. So, what happens? There is a huge amount of interference, and what we have is a crosstalk appearing in the I channel and the Q channel. So, what happens? The in phase produces a component on the quadrature phase and the quadrature phase produces a component on the in phase. So, as there is relative phase offset between these two, this is also sometimes known as, no, this is not the IQ imbalance. So, because of the phase offset between the transmitter and the receiver, some components of the I channel gets projected onto the Q and some components of the Q channel gets projected onto the I. So, there is crosstalk, and this not only causes interference, the desired signal power is reduced and interference power increases as there is gap in phase. So, one could also easily say that as the carrier frequency offset increases, you get a similar effect, right, because ultimately it is the phase. So, this at least tells you why this phase offset between the transmitter and this receiver has to be estimated and compensated at the receiver. If we do not compensate, then the performance will be unacceptably poor. All right. So, next let us look at the MLE estimation, ML estimation of the carrier phase. So, we have already done such a thing in the earlier discussion when we just finished the discussion on MLE estimator. So, we have inadvertently already addressed this problem. So, we will now see this problem purely from the communication perspective. So, things will be easier for us since we have already discussed partially this. So, the received the ST is this model which I do not need to explain, which you are well aware of, and received signal is the transmitted signal which is parameterized by the phase, and there is a noise term, and the likelihood function is also we have explained since it is the vector r, and we said the components of r are independent being affected by Gaussian noise. This we have discussed several times. The joint PDF of r conditioned on psi is the parameter vector to be estimated. In this case it contains only the phase is given by the expression here, and of course the nth component is found by taking the RT on the basis function. So, it contains the signal which is the component of the signal on the basis function. So, we have discussed all these things, right. So, we could also say that you could expand this expression if we have large dimension as n tends to infinity to a continuous function, right. So, you could actually take, instead of these components, you could write it in terms of this expansion, right. You could write in terms of the signal directly instead of taking a summation over n. If you have taken all the components, then you could write in terms of the integration. So, the likelihood function that may be considered now is this, right. So, we have, instead of the summation, we have gone to the integration. The log likelihood function, we have stated you can use the log likelihood function. If you take the log likelihood, then the exponent goes away, this becomes the direct cost function. So, that is what we are interested in. So, we have RT. So, there is a square term, you are going to have an R squared term, you are going to have an S squared term, and you will be having an R multiplied by S term with a 2 in front of it. Now, R squared term we have already discussed several times, is not necessary. S squared, if it is a constant modulus signal, is also irrelevant, rather the most important term is the cross correlation, right. Further, because when you square, you are removing the phase component from it. So, when you take this expression, the log likelihood function, the way to find the phase is to take the derivative of the log likelihood function with respect to 0 and get the solution. So, you write the derivative of the log likelihood function with respect to the phase set to 0 yields the solution. That means, we could say that the derivative which is integrate over the period t0 RT, when you take the derivative of this, you get cos becomes a sine, you get the expression which looks like this. So, now there is a very interesting turn of things how we look at this expression as we have got there. What we say is, suppose phi is the ML solution, maximum likelihood solution. If phi is the maximum likelihood solution, then what would happen? Put into this expression the maximum likelihood solution, this integrator should turn out to give a value of 0. This is a bit subtle, but we use that. So, let phi ML be the phase which maximizes the log likelihood function. So, that means the first derivative of log likelihood function at phi ML should be equal to 0, and hence it is a solution to this expression, that is equal to 0. So, what we do is we write the expression as we had seen before, but except instead of phi we put phi ML, and then we say that this is equal to 0. That means, if I put phi ML in this, this is equal to 0. Now, this motivates the solution that instead of actually solving this, you could find a PLL like structure, a loop like structure. So, what you do is you have RT as the received signal, you multiply by some sinusoid with certain phase, you integrate it, right. Once you integrate it, you feed it to the VCO, right, and this would settle in such a way that it produces the phi for which this produces a 0 error term. This integrator motivates this PLL solution. So, what you can think of is R of t is cos 2 pi f c t plus phi. So, the error term is cos 2 pi f c t, which is R t coming in, multiplied by sin 2 pi f c t plus phi m l. So, that is produced by the VCO, right. So, this product can be factored as half sin of phi minus phi m l, because they have the same frequency, that is what we have assumed, plus half sin 4 pi f c t plus phi m l. Now, since you are passing through the integrator, right, this acts like a loop filter and it filters out the high frequency component. So, what is left is just the sine of phi minus phi m l, and if this angle is very small, this can be approximated as phi minus phi m l, and this is the error term which drives the VCO, right. If the error signal is 0, the VCO produces 2 pi f c t, and if it produces a certain voltage, it is going to produce sine 2 pi f c t plus a phase. So, the input signal, the error term is going to drive the VCO. So, in this way you could realize a carrier frequency synchronization. Just to remind, one could also get the phi m l as stated in this particular expression, which we had used in the previous discussion when we did sinusoidal phase estimation. The only difference here is we have used the integration instead of a summation. So, in the earlier picture that we had referred to, here, so the summation is replaced by an integration. So, that is what you have over here. So, you could get a single shot estimation of the carrier phase, whereas here through a loop you are able to continuously track the filter phase, right, the received signal phase. So, if this phase changes, if the received phase changes, this will be able to track the phase again. So, now we move further to discuss the carrier phase recovery of a modulated carrier. So, till now we have seen that you have a signal which is unmodulated, we just have cos 2 pi f c t plus phi, but now we say let there be a modulated carrier. So, for the modulated carrier, what we will refer to is in this case where A is not constant, but it is fluctuating with time. So, in all the previous cases you would have seen that we have taken the received signal as cos 2 pi f c t. Now, there will be A in front of it. So, if there is an A in front of it, in that case the integration output that you will get is going to go hayway, because the modulation which will be A in front of it could take a plus and minus values, and the integration could result in a 0. So, when we have a modulated carrier, so S of t contains modulated information, that means it carries information through, let us say, the amplitude. So, in recovering the phase of a modulated carrier, one can assume that the sequence in is known at the receiver. So, in this case it is pilot sequence or data aided, as we have discussed for channel estimation. So, now you see that how the pilot is also important for carrier recovery if it is available. The other option is you treat in as unknown, and the other option, and there are two options in case of being known, one is pilot, the other one is decision directed, right. Decision directed means that we decode in, the transmitted sequence, and we assume whatever we have decoded is correct, and we use it back into the estimation procedure. So, without delaying further, let us go into it. So, in the decision directed mode, the low pass equivalent received signal. So, we are directly jumping to low pass equivalent, we are not going through the pass band as usual we have done before. There is a phase term which is available, right. So, we are still talking about carrier phase recovery. Now, please note that carrier phase is very important, because if we can match the instantaneous phase, we have actually matched the total phase of the carrier. So, that is sufficient. So, this could be summation in, which is the transmitted sequence, and the pulse, and there is of course a noise, and this is the residual phase, right. So, we could write this as the transmitted sequence with a residual phase e to the power of j phi, and there is noise. So, now this S L of t, we could assume this to be a known sequence, right, either by means of pilot or by means of decision directed, which we will see shortly. The likelihood function would be some constant term e to the power of real part of this, which we have seen before. In the previous expression, we have been looking at the likelihood function. So, it is not new. So, we did explain here that you have this square term, r squared is not relevant for S having constant modulus, again this is not important. So, we are left with the product term. So, we have this expression that is important. So, and the square remove the phase component of S. So, that is not going to help. We are related only with the correlated term. So, we have RLT SLT e to the power of j phi, right. If SL is complex, you can take the complex conjugate, and the log likelihood function, this is the likelihood function. The log likelihood function is going to take the inner part of it, which is left in this fashion, right. Now is the important part. So, we will substitute SLT, because we know it, we assume we know it, and assume that T0 is equal to KT, that means the observation interval. So, here we first time introduce that this T may be unknown, which we will address when we talk about timing synchronization. So, when we replace SLT in the previous expression, so we had SLT, right. So, SLT we replace over here is IN, because you can clearly see IN, right. So, SLT is known, we have RL times this, right. So, basically this is the gate function. So, now if you carefully look at received signal, right, projected onto the basis function in the baseband. So, what you could write this component as the output of the matched filter, which is the YN. We had a similar situation earlier. So, we are just using our earlier knowledge appropriately by studying the expression, what it means. So, YN is the output of the matched filter. So, now if I take the derivative of the log likelihood function, set it to 0, we can get our receiver. So, you do the same procedure, you take the derivative of log likelihood function with respect to phi and set it to 0. By doing so, we can get an expression which is negative of tan inverse imaginary part. So, because when you do this, it has a real part over here. So, when you take the derivative of this, you are going to get an expression which looks like this. We are, due to time shortage, we are pre-writing the equation. So, if you do a few steps, you can arrive at this expression, right. And when this is set to 0, naturally you get an expression which looks very familiar to you. So, but now we have the real part and imaginary part, and we have IN star and YN. So, earlier you may remember the expression had an XN and a sine, and here it was XN and a cosine. So, which we are again reminiscent of this kind of expression. So, they are all very similar, because we are using the similar signal model and we are using the log likelihood function and finally the ML estimator. So, in this way we could translate the expression that we have seen in the previous page, that means that we have here expression that we have above, to a block diagrammatic representation, receive the signal, right, integrate it, sample it, get YN. So, that is what we had, YN, Y1 was here, and how do you get YN? Received signal, integrate it with the basis function. So, you integrate in case of rectangular pulse, if it is rectangular you just need to integrate, sample it and get YN as we have here in this part. So, once you have yn, you would do an amplitude detection and you would find in star. So, that is has been detected. So, this decision directs the phase later on. So, this is that in that we have detected. If it is known a priori, it could be pilot, otherwise it could be decision directed. So, moving further, so using yn and in is what you need to estimate the phase. So, if you look at this, you just need the in and the output of the matched filter. So, if you do this, you can estimate the phase. Once you have estimated the phase, you pass it to the carrier generator. The carrier generator multiplied by the pulse generator is what is multiplied by the received signal. So, that is what you have. The pulse generator is GT, right, and once it passes through this filter or this integrator, you are left with the residual phase, and the expressions of this finally yielding to this has been translated to a block diagrammatic representation which is realizable. So, we stop the discussion on carrier recovery at this point, and just trying to summarize that we have started with the philosophy of estimating signal parameter, we have used the log likelihood function, and we have made a parameter estimation using the maximum likelihood estimator. So, when we have finally arrived at the last phase of the estimation, the very important task remains over there is to read the expression carefully and try to see how the signal at each stage gets processed. Processing in the sense multiplication, integration, summation, trigonometric like tan inverse and so on and so forth. So, we translate each part of the equation to the corresponding block diagram to realize the carrier phase recovery loop. And since there is a loop over here, we generally call it the carrier phase recovery loop, and you can see that matched filter is already part of it, detection is already part of it. So, using detection, feeding it back to the whole cycle. So, we have the the carrier recovery at the receiver. So, once again I would like to remind you about the most important thing to take from these is the use of maximum likelihood estimator, and before that the effect of phase. So, that is what is very important in terms of evaluation, and the rest of what we have discussed is very important in terms of designing a appropriate receiver which can do carrier estimation. In summary, you have now been exposed to channel estimation, and you can now also estimate the instantaneous carrier phase, by virtue of which you can almost build a receiver. The last thing which we will look at in the next lecture is symbol timing recovery, which will complete the essential components required to build a complete communication system. Thank you.